Theorem 9.7 is a big one. The measure of an inscribed angle is half the measure of its intercepted arc. Let's take a second to think about what this says first, and then I'll give you some reasons to believe it's true. So in this case, we have an inscribed angle. Remember, inscribed means vertex is on the circle. So since this point B is on the circle, and points A and B, of course, over here are as well, that angle, angle ABC, is an inscribed angle. And right now, that angle is around 42 degrees, but obviously we can change it here by moving this around. The theorem says there's a relationship between the measure of that angle and the measure of its intercepted arc. And let's see what Sketchpad says the measure of the intercepted arc is. Okay, so just by quick experiment here, you can look at these numbers and you might realize that there is something nice going on, that the measure of the angle seems to be half the measure of the intercepted arc, which is, of course, what the theorem says. Now, why would that be true? Pretty challenging to see why. Now, let's go ahead and prove the easiest case of this. I'm going to go ahead and make this chord a diameter. And this doesn't take care of the full proof here, but it gets you the idea behind it. Maybe we can think about the other cases. So here is a particular case of this proof, of this idea, that here we have an inscribed angle. The angle that's inscribed is ABF, and here is the intercepted arc. And we think that this angle is going to be half of that intercepted arc. And this is a very specific case where this particular chord happens to be a diameter. But again, it's going to show you the basic idea. So I'm going to prove that that angle is half of that arc. And here's how I'm going to do it. Let's draw this radius. And let's think about what's true about this angle versus this arc. If this angle has, let's say, x degrees, then this angle, this arc right here, is also going to be x degrees. The measure of a central angle is equal to the measure of its intercepted arc. But we also know that this triangle right here has to be isosceles. The triangle BDA must be isosceles because those two legs right here, BD and DA, are radii of the circle. So the angle right here at B and the angle right here at A must be congruent. And at the same time, we know that the angle at B and the angle at A must add up to this angle right here, because the exterior angle of a triangle is equal to the sum of its remote interior angles. So what we know, therefore, is that this is 1/2 of x right here. Oh, that doesn't look very nice, but that happens to be the measure of that angle. And this is also 1/2 of x, which is exactly what we were trying to prove. This angle over here at B must be 1/2 the measure of its intercepted arc. So it turns out to be true.